My friends, this is where we're starting today with the one of two new things. Both of these are just a quick introduction. This one, acid-base indicators. We are familiar with just one type of indicator in this class that we've used. Anybody remember what it's called? Phenolphthalein it is. Yeah, phenolphthalein is the indicator that we use for, we used it a couple of times earlier in the year, standardizing a strong base solution with like KHP, if you remember doing that. That's one of many indicators. There's a lot of indicators out there. This is another one. Now, I bet you remember doing an experiment in your biology class that used this indicator. Back when you were in 9th grade bio, which may be a stretch for your brain to go back that far, but you did an experiment there where I think the teacher put some algae into a test tube with some water and then put some BTB, bromothiamyl blue, in there, and it changed from yellow to blue. You remember that? They were trying to show you about respiration, plant respiration? Yes? They actually may have even passed a flask around the room with every student having a straw and blowing your exhaled breath into the flask. And that changed the color of the indicating water too. Because when you blow exhaled CO2 into water, it causes it to become acidic. And so you'll get the acid color of bromothiamyl blue. The way it works is like this. When it's a base, when it's in a base, the indicator doesn't have its hydrogen on it, and without the hydrogen, it's blue. When it gets into an acid environment, it puts its hydrogen on, and it's yellow. That's the way indicators tend to work. They'll be a different color with their hydrogen on them than they are without their hydrogen on them. Because almost all indicators are weak acids themselves. Now, do you remember how much phenolphthalein we put into our flask when we were going to start titrating? 2 to 3 drops. Yeah, 2 to 3 drops. Not very much. When you put 2 to 3 drops into 10 milliliters of solution that you're starting with, that kind of gives away that the indicator is not affecting the reaction. It's not getting in the way of anything happening in the reaction. All it's doing is providing the color for you to tell whether it's in an acid environment or a base environment, or whether you've got to the equivalence point or not. So the indicator should be there to indicate whether you've hit the equivalence point. Remember that the indicator itself is not affecting the acid-base reaction. So you have, I mean, I know that this is an acid, but you don't use an indicator as an acid for a titration. You just have a drop or two in it of the indicator in the solution you're titrating, just to give you an idea of where it's at. Okay, now what do we do with this? Why would you see that? I actually have a little derivation of how the indicator works, but I've found over past years people don't really understand it anyway. So if you want me to explain this through the derivation, just come up to me like after class or whatever, and I'll show it to you. I can tell you probably still won't understand it, but don't write anything until I tell you to. So I started this thing, defining the Ka of the indicator and all that, a little bit more, and then there's a little bit more, and then eventually we come to these two statements, and this is good enough for what I want you to write down. An indicator should tell you when you've hit the equivalence point, and it does it by this. The color of an indicator is going to change. Remember, an indicator itself is a weak acid. So the pKa of the indicator, plus or minus by 1 pH unit, is going to tell you, or that's where the color change is going to happen. So when you're using it to indicate another acid-base reaction, this part in blue is what you want. You want to choose an indicator that's going to change color, have its pKa close to the equivalence point pH. So an indicator should be used to tell us when we've hit the equivalence point. So we want to match up an indicator with whatever the reaction it is that we're trying to get that information for. Let me show you something that's in the book. This is right at the end of the buffer chapter. This is page, you can read it, 746, and it's a sideways table, so I'm going to turn it sideways like it should be. And across the top we see the pH scale from 0. It's up to 14, but I'll just leave it over here so we can read maybe what the names of the indicators are. So I want you to see that there's a whole lot of indicators out there. Phenolphthalein is not the only acid-base indicator. There's a bunch of them. Well, there's bromothiamyl blue, of course. And so this table tells us what pH these indicators change color in, and actually what the colors are that the indicators have. So one common one is methyl red. Methyl red is red when it's in an acid solution, but when it gets up to about 4.5 or so, it changes to yellow. So if you're running a titration that has its equivalence point around 4.5, you would use methyl red to indicate that. So as soon as the color changes over, you know you hit the end of the equivalence point. You would not, if you had something that changed pH at 4.5, you would not want to use phenolphthalein. Phenolphthalein is way down here. And phenolphthalein doesn't change color until it's just over 8. Right about a pH of 8 is where phenolphthalein would change color. So if you're using phenolphthalein in this titration that has an equivalence point of pH of 4, then you're going to totally miss. It's going to change color, but it's going to be way after the equivalence point. So we want to match up which indicator will work with the pH of the equivalence point. That's really how we do it. Notice that phenolphthalein is our indicator of choice, yet it doesn't change color until it's above 7. It's above 8. It's above 8 when it changes color. Is that a problem? And the answer really is no, especially when we're titrating a strong acid with using phenolphthalein. Because the titration curve vertical part is so big, it'll go through pH of 7 and through pH of 8, 9, and 10, all pretty much on the same drop of the sodium hydroxide we're adding to it. Probably a better indicator to use would be phenol red. Phenol red is going to change color right at a pH of 7. There's my 7 line. And right there on that 7 pH is where phenol red is changing color. The problem with phenol red is that when it's in an acid, it's yellow. And when it's in a base, it's red. But what's between yellow and red? Orange. Right. Is there more than one shade of orange? Yeah, that's a problem. When you start seeing some orange, so you see it start going like by drops or half drops or whatever, and you'll get to an orange. But then you'll add another half drop, and it's a different color orange. Well, which orange is the equivalence point? I don't know. So even though this is changing color at 7, it's not that great because you don't get a good clean transition. That's why phenolphthalein is nice. Number one, it's nice because it's cheap. I'm not going to kid around about this. It's cheap to buy. But the second thing that makes it very nice is that it's either clear or it's pink. And you can absolutely tell the difference if it's clear or pink. So that's what we also like it for. Some of these are interesting. They actually change colors twice. And this one starts red, goes yellow, and then it goes back to red. Interesting. Now, when I give you the quiz on this chapter, I'll give you this. It'll be on a photocopy, so you won't have the colors on it. But I will not ask you what color. I'm not going to say what color is a bromocresol green at a pH of 4. On a black and white paper, that's rude. So you don't need to worry about any color. Don't memorize anything on here. But I would ask you, okay, coming after me. I might ask you, here's an acid, a weak acid that's being titrated with sodium hydroxide. What indicator should you use? Well, what you're going to have to do is figure out what the pH at the equivalence point is and then match up something that changes color close to that equivalence point. I would say the pH of the equivalence point plus or minus 1 pH unit is what you want to look for. So let's say you have, and I have actually another slide that does not present it as nice as the Zoom calls do. The next slide on here has this. So if you have a titration in which the equivalence point pH is 5, what indicator should you use? Well, it looks like this one we probably don't want to use because that goes between about 3 and 4.5 or so. This one is from 3.8 to 5.4. So this one would be a good one to indicate a pH of 5 equivalence point. This one would work too, Methyl Red. And then even this one is fine, from 5 to 6.4. You have the pH plus or minus 1, so that would be fine. Anybody have any questions about that? Now, there's not very many homework problems about indicators. There's a couple. So try those out and see. I think it's pretty easy to figure out which indicator. You just have to know how to choose your indicator. You got to find the equivalence point pH. Okay, so that's the first thing that's new. The second thing that's new, whoops, I got a bunch of writing on this. I want to start over on that. The other thing is, is this yours? Oh. We'll do this in the lab that we're going to start tomorrow. We won't get to the diprotic tomorrow, but the titration of a diprotic acid is going to wind up giving you a curve that looks like this. It's going to have 2 equivalent point vertical regions on it. And the reason is because of this. So we have Ka1 and Ka2. We're going to hit this equivalence point for this reaction. And then we keep going and take the second hydrogen off. We'll get this equivalence point for that reaction. So you get 2 bumps in the graph. And plan on one of your bumps being pretty weak, wimpy. Like you see, this is a small, but we'll be happy to have a bump like this. Often, it'll look like this. Where one of your equivalence points would be very obvious, but you might get something like this and think, shoot, is that my equivalence point, or should I be waiting for another one back there? But yeah, when you get like just a change of direction, I call that a point of inflection. You get the inflection kind of right there where it starts going up, and then right there where it starts leveling off. Just find those 2 points and just take the midpoint of them. That's good enough. So be ready for a wimpy equivalence point indication like